Здравствуйте, небольшое интро, вступление сегодня. Я надеюсь, вы все помните, что в первом модуле у вас были прекрасные модераторы в лице меня и Пети, и кажется, что это было очень полезно. И мы бы хотели, чтобы сегодня вам тоже помогали некоторые прекрасные люди. Это Саша, Ярослав и Соня. Машите, пожалуйста, ручками. Они учились вместе со мной в Сколково, тоже, ну, если вам будет интересно про их бэкграунд, можете, наверное, расспросить лично. Но вообще сегодня во время рабочих сессий они будут помогать вам и ходить по комнатам, так что можете обращаться к ним со своими вопросами, так же, как к Алексу. Спасибо.
Thanks, Sophie. Very excited to have some moderators with us. Just so you all know, we've brought in some extra technical support. So while we're doing our team breakouts, everyone gets a little bit of extra help in that sense. I know last week we had some technical difficulties with Anaconda, with Jupyter, with Python. Completely expected. It's frustrating the first time you get used to it. Getting it installed, getting it ready to go. By the end of today, I'm certain we will have all of that resolved, especially with the extra help we have from our moderators today. So very excited about that. In terms of what we're going to do today, we'll do a brief recap of some of the material from last week, and I'll walk you through the solutions to that smoking exercise I posted. That way you can see how I approached it, see some of the code I used. That's also shared on Canvas, so everyone has access to that code. And I'll continue doing that throughout the course, so you always have my code that you can use to run through those exercises. And then we will move on to today's material, which is focused on databases and SQL. SQL is another programming language, a very, very simple programming language. We're going to use SQL inside Jupyter Notebooks, so no new software today, but a new language. And SQL is, I think, the most important tool for citizen data scientists out there. It is going to be the most frequently used language to access data, to manipulate data, and to do simple analysis. One of the reasons we're starting with some intro Python, some intro SQL, is because sometimes that's all you need. I think that there's a lot of hype around artificial intelligence, very advanced techniques, deep learning. But my experience is that sometimes really simple analytics can drive a lot of value with not a lot of complexity. I'll give a couple examples of this from my own career. As a big Canadian bank, we have about 14 million customers. We obviously have a website and we have a call center where you can call in and ask for help. And our call center is very, very expensive. Tens of thousands of employees just answering phones, talking to customers. So anytime we can reduce the call volume, we save lots of money. We get to use those people much more effectively. Well, with some very simple analysis, all we had to do was match up Alex phoning into the bank and what web page he was currently browsing. We could figure out which web pages drove traffic to the call center. So were web pages confusing? Were they telling people to call the bank for some reason? This was done in Python, using some of the techniques we discussed last week and some we'll discuss this week, to line up those events, to join them together, to give us a full picture of how a customer was interacting with us. No predictive modeling, no machine learning. And we were able to drop call volumes substantially, double-digit percentage call volumes down. It saved us millions and millions of dollars. And it just took a few data scientists and some intro Python material. So this is the foundation. If your organization is early in its data science journey, early in its analytics journey, this is where you start. This is where you get some wins start tracking some value, and then get the sponsorship you need to spend big dollars on data scientists and big infrastructure, et cetera. So lots of value coming out of these things. We did another project very similar where we were using these techniques to try and figure out if a customer would not be able to pay back one of their loans on a credit card or a mortgage. And it turned out that there were some very simple signs you could find in someone's checking account that would tell you about this. Is their checking account balance going down every month? Are they late on a payment somewhere else? So very simple data aggregation, data exploration techniques, giving us lots of insight into a customer's life. Again, without having to go down the complex predictive modeling path. So with that being said, we will do some predictive modeling. It's lots of fun. It's very exciting stuff. But a well-rounded approach to analytics has been much more successful for me than leaning heavily on complex techniques. On Thursday, we'll be talking about data visualization and storytelling, which I think is an equally important concept in this space. Because what we're studying is hard, it's complex, it's not easily explained. When you're going around your organization trying to talk about this, you're going to need some of the tools to explain it simply, because no one is going to want to see a Jupyter notebook. No one's going to want to see the Python you wrote when they're trying to make business decisions. So we'll talk about that. We'll pull it all together next week. With that, let me jump into the Jupyter notebook, and I will show you that smoking exercise solution. So here I have, in this first cell, me importing the smoking data. This is the same code we saw last week, where I've got my smoking data, which is an Excel file, saved in the data folder in the same directory as this Jupyter notebook. All I've done here is I've imported the data using that pandas read Excel function, and I've printed out the first 5 records here. The first thing you're going to see about this data is that it's very big. So I've only printed out 5 rows, but there's 195 columns. That's way too much data to look at, right? Even as you scroll across here, way too much to see. For some background on this data, this is real data produced by a survey a university here in Canada did. So this survey was sent out to university students at one of our big universities here, and it asked them information about smoking cigarettes. How often do you smoke? When do you smoke? How many days a month? This survey data was published with a data dictionary for anyone to analyze. There were many, many records. I shortened this data set a little bit, so it's a little bit easier for us to work with. But that's why there's so many columns. Each column refers to a question in the survey. So it's real data that you're working with here. And when we go in and describe it here, we can see, okay, there's about 2,000 records in total. That's the count. And as we go through here, we can see the average age of our respondents. We can see a number of other responses, but really, we don't know what these columns are. And if you remember last week, we talked about the first step of data exploration being to understand what's in each of your columns. That's why I posted the data dictionary to go along with it. And what I'd like to say about that is, this is the best case scenario for data. When you get a data set that's pre-cleaned with an awesome data dictionary, it virtually never happens in the corporate world. It is so hard to get data this clean with great metadata, great explanations about what's happening. So the first thing I asked you to do was to create a histogram of the variable SLST30A1. Again, no idea what that variable is just yet, but I asked you to create a histogram. To do that, we're going to use a library called matplotlib. You would have seen this in the data exploration cheat sheet from last week. And if not to worry, we'll spend time today in our breakouts going through that again. And we just need to use the command hist, short for histogram. A histogram is a great way of understanding the distribution of a single variable. And in this case, what we're seeing is maybe 200 records between 0 and 10, and then everything else between 90 and 100. Seems a little bit strange. Doesn't seem quite right. It's not what I expect to see from a histogram. Now, when I open the data dictionary here, I'll read a few of these things out. This was what was shared as part of the data, and it gives you information on each variable in the data set, what that variable means, and what all the values mean. In this case, SLST30A1 refers to the number of days you smoked one or more cigarettes last month, the number of days in the month. And we can see here that the values are either 1 through 8, which represent some number of days, or 96, which they call a valid skip. Now, in survey design, a valid skip generally happens when you don't need to answer a question. You might imagine the question before this was, have you ever smoked a cigarette? If the answer to that was no, then there was no point in asking you how many cigarettes you smoked last month. You wouldn't even be presented with this question. That's what a valid skip is. And what this is trying to tell us here is that of all the respondents, the vast majority of them got a valid skip, which makes good sense when we're looking at our data here. So these are records that actually aren't very useful to us. They're not giving us any information about the number of days you smoked a cigarette last month. So the next thing I asked you to do was remove all those 96s, remove the bad records from this data set. And to do that, we're just using some Python logic to reference a column and a condition that we need to be true. In this case, what I'm saying is create a new object called smoking fixed and make that equal to smoking data, what I originally imported, where the column SLST30A1 is less than the number 96. You can save this line of code and modify it to suit any purpose you need. So change your data frame name from smoking data, change your column name to whatever column you want to filter on, and then change your condition. In this case, I have less than 96, but you could make it equal to 1 or greater than 5. Anything you need here, you can put in, get a new data frame that's going to meet those conditions. This is called filtering. Again, this code was available in the data exploration cheat sheet from last week. And we can see now that when we run our head command, our row IDs have changed fairly substantially. We went from every record, 0, 1, 2, 3, 4, to now some very select records, only those records that had valid entries in that question. That means we went from about 2,000 records down to 142. That's what we're working with now. Now, when we rerun our histogram, this is the exact same code I had above. All I've done is I've changed the object. We can see a much different histogram, and one that tells a bit of a better story. On the left-hand side here, we have people who smoked at some point, but have quit. People who aren't smoking anymore, or didn't smoke last month at least. And on the right-hand side, we have people who smoke every day. And then a bunch of people throughout the middle. The last thing I asked you to do was to recode all of the values in this data set based on this data dictionary. So change the value 2 to be 1 day, and change the value 3 to be 2.5 days, so that they actually correspond with the number of days and not just a random value someone chose for the survey. This is the code I use for that. This just sets up a series of pairs. This says anytime there's a 1, make it a 0. Anytime there's a 2, make it a 1. Again, copy and paste this code, reuse it as you need to. All you need to do is change these pair values and change the data frame you want to make those replacements in. And that's the smoking exercise. Again, we can see the last histogram here. This code's available on the portal, so definitely recommend you download it, give it a run. As long as you save the smoking data, just like I showed you last time, this code should run automatically for you. So save it in that data folder in the same directory. Okay, let me pause here. Questions about this? Anything I can explain in more detail? I apologize for that. We will do a better job at getting some of these translated ahead of time. So I'll keep that in mind for classes going forward, and we'll figure out everything that needs to be translated. What is the experience like reading the Python code? I know the code has to be in Latin text, and it's sort of English based, but sort of also made up words. Is that going okay? Okay, well, if people are struggling with any of the code, we've got the breakout later today. And of course, you can always send me an email if you're struggling with anything, and I'll try and help you debug and troubleshoot that. On to today's material. A couple questions in the chat here. Vladimir, could you help me out with those? Mm-hmm. Yeah. Okay. So two comments in the chat that are worth talking about. One is that it takes a fair bit of time to find the code, get it set up right, and that is absolutely true. You will get much faster, and as you work through the program, as you have to do more complicated programming, you will get very fast at this. I promise. At the start, it is going to be slow. It is going to be hard, but it will get better. The second question was, why do this in Python at all? Why not just do it in Excel? There are two good reasons for this. The first is that Excel has limits that Python does not. Those limits are around data size. So Excel has theoretical limits for how big a data set can be before it crashes. But the more important one is around computation speed and capabilities. I've had many Excel spreadsheets that just stop working because they've got too complex, too many calculations, etc. And when you want to start doing more complex analysis, it can't happen in Excel anymore. You can't build a machine learning model in Excel. It just doesn't work. Python becomes much, much faster, and it becomes the only tool you need. One thing you will not want to do is move data back and forth between different pieces of software over and over again. It's very cumbersome, and it means that no one else can follow what you did. One of the big challenges in this space is collaborating effectively. And if you do a couple things in Excel, save the file, no one knows what you did, then you run some analysis, no one will be able to reproduce that. And when you're talking about something that's new, that is exciting, it also makes people a little bit nervous. And you need to be able to reproduce everything you do. You need to give people confidence that this is reliable. So Python will become this one-stop shop for all of your data analysis needs, instead of having to go from software programs to different software programs. Using Excel right now will seem much easier, only because it's what you're used to. Eventually, both will seem just as easy. Okay, let's talk databases and SQL. As I said last week, data is really the heart of what we do as data scientists, as analytics professionals. And without good data, we can't do anything at all. So it's very important to understand a little bit about where to find data, how to get access to it, how to clean it up a little bit. What we're going to talk about today is a little bit of database design. This is important just because it sets us up well to think about how to pull data out of databases. Most of you are not going to do database design. I don't do database design. We hire people who are very, very good at this, data engineers, to set this up. But you need to understand some of the principles to make writing SQL queries that much easier. And then we'll talk about SQL itself. I'll show you all the basics you need to get started. And then we'll do some SQL exercises. You'll get a little bit of a chance to practice. Let's talk a little bit about data. I like to start this conversation just talking about how much data is produced all the time. This infographic represents how much data is produced every minute of every day in 2021. I'll read out a couple of these that I think are important. Amazon customers spend $283,000 a minute, every minute in 2021. 12 million people send an iMessage on their iPhones. 575,000 Twitter tweets. Amazing amounts of data produced by all of this. And what I like to think through is there's the sort of obvious data that's generated when you do something. Let's talk about making a purchase on Amazon. There's some obvious data that you give to Amazon, right? You give them your credit card information, you give them your address, they know what you're buying, so they know the product. But then there's all of this extra data that gets collected as part of this process. So when you order something on Amazon, people in a warehouse go and find what you ordered. Robots go and do this. So now we have information on what's going on in a warehouse. Your product also gets delivered. So there's a delivery company that's sometimes owned by Amazon that's driving around the city delivering packages to you. And through that, they get data on traffic patterns, on how many people are ordering from Amazon in certain areas, geospatial data. And when you think about just how much data is produced, it all needs to be stored somewhere. Some of this data is unstructured, so it's hard to store in a traditional database, but it's all incredibly valuable. And the companies like Google, Amazon, Facebook, Netflix that have learned how to use that data very, very effectively, they're the ones that are driving massive value. Amazon making product recommendations, Netflix telling you what to watch next, all powered by machine learning, all powered by this data. You're trying to understand more about you and make predictions based on that. We spoke briefly about structured and unstructured data last week. Just a few examples here. Structured data, largely what we'll be working with in this course. This would be financial data, credit card data. If you submit a form on a website, structured. Unstructured data, basically everything else. Anything you can't fit in Excel, unstructured data. This could be videos, it could be websites, emails, social media, satellite photos, all sorts of any other data that doesn't fit in a table is going to be unstructured. And unstructured data comes with its own set of challenges, its own technology, its own style of databases, its own techniques from an analytics perspective to work with. The one thing worth saying about unstructured data is that your first job with unstructured data is to structure it. So the techniques we learn working with structured data here are going to be very important throughout the analytics lifecycle, because even if you have unstructured data, you're going to be trying to fit it into this tabular structure. That might mean that when you get a picture of something, the first thing you're going to do is try and figure out what's in that picture. Structure the information that way. Same thing with text files. So you might see tweets and want to understand whether the tweet was positive or negative, or whether it was about a certain stock. That's structuring the data. We also spoke briefly about big and small data. And big data is another one of the buzzwords out there right now as it relates to analytics. The first thing I want to tell you about big data is it is a marketing term. IBM made it up. There is no such thing as big data. There is no threshold after which your data becomes big. But there are a few ways we can describe big data. We do that with what we call the 4 V's: volume, variety, velocity, and veracity. Again, no thresholds. There's no certain volume that makes your data big, but as you move up in the 4 V's, your data becomes big. There's a few that are worth talking about. Volume is an easy one. It's just, we produce a lot of data today. I was speaking with some colleagues this morning at RBC. We process over 100 billion transactions a day. That's high volume, lots and lots of data. Variety speaks to the different types of data that's created. And this one seems fairly obvious. We produce images, we produce text, we produce transaction records, and we do it at the trillion scale. So lots of variety of data. But velocity and veracity are the most interesting. Velocity speaks to how quickly data is generated and how fast you need to act on it. So think about a self-driving car. Very, very high velocity of data. Sensors all around it, taking in that information, trying to make predictions about what's going to happen half a second from now. Very hard to work with high velocity data. And veracity, can you trust the data that's coming in? It's coming in fast, there's a lot of it. How trustworthy is that data? Are people lying on surveys? Is the data dirty? Is it coming in a strange format? So very hard to validate data in real time this way. An example here is, imagine applying for a credit card and getting an instant response. Very hard to determine whether or not the data you're getting is reliable. And you have to make a decision right now. So very difficult to work with. Later in the program, you'll talk a little bit more about working with big data. There's a specific tool inside Python that's very popular for this called Spark. It's sort of another programming language, and it's excellent at working with very, very big data. But it's really just one step ahead of what we're working with now. Okay, data models. I'm not going to spend a lot of time on data models, but this is how we think about the structure of data in databases. We use something we call the entity relationship diagram. So if you think about a big database at your company that stores all of the useful information you need, there's going to be tables in that database, many different tables with many different pieces of information. When someone designs a database, they think about two things: entities and relationships. Entities are things that the business wants to track. These are loosely tables in a database. And relationships are how those tables connect to one another. This is a really important concept when it comes to actually writing SQL queries, because those relationships are going to be how we pull data out really effectively. Entities have a few components. They always have a name. What do you name your table? They have a unique identifier, so some unique key that identifies that table. They have attributes. This is everything you would include in your table. We could think about having a customer table that has all of our customers' name, address, phone number, etc. And of course, these have relationships to other entities. So customers can have orders, for example. If we think about a customer and an order relationship, customers create orders and orders belong to customers. And there's a very specific style of relationship here. So a customer can have any number of orders. You could have no orders, you could be a brand new customer, or you could have 100 orders and be a long-time customer. But an order can only have one customer. We refer to this as what we call maximum cardinality. This speaks to the maximum number that a relationship can have. There's also what we call minimum cardinality, which is to say a customer can have 0 orders. That's the minimum number. But an order must have a customer. You can't have an order without a customer. So we build up these relationships very, very carefully to make sure that we never have data that doesn't line up appropriately in a database. There's a few different examples of these. A customer has a single account. An account always belongs to a single customer. That's one-to-one. You can never change the numbers that line up there. Now, of course, this is just an example. There may be organizations where customers are allowed to have multiple accounts. It's just a single example, and you get to define this as part of how you structure your business and structure your data storage. A many-to-many relationship, an order could have one or many products, and a product could exist in one or many orders. And of course, one-to-many, this is the idea that some have, customers have no orders, or customers can have many orders. And this is the set of symbols that we use to describe those relationships. So I just wanted to give you a little bit of background on database design. As I said, most of you will not get involved in database design, but understanding how these relationships are built up are really going to help when we think through a concept in SQL called joins. So let's talk about relational databases and SQL. First, a little bit of terminology. We have tables. This is just like those entities we spoke about in database design. All tables have columns. They run vertically, and rows running horizontally. You can have as many columns, as many rows as you want in a table. Some get quite wide. When we looked at the smoking data, we saw that there were over 250 columns and thousands of records. And we try to set these up so that there's very, very little overlap between tables. So we see department and employee here that have sort of one level of overlap in the ID column, and that's it. We'll come back to that in just a minute for why it's so important. Now, relational databases refer to the idea that we use multiple tables, we join them together, and that allows us to very efficiently pull out very wide records without duplicating data. I'll show you how this works. Imagine we have 3 tables here. We have one, which are students in a class. We have one, which are courses that a university offers. And a third, that's enrollment. So this is when that course actually takes place. By using some of the ID columns in these tables, we can line up all the data and figure out what classes Alex is in and when. To do that, we take our student ID and we line it up with the student ID row here. We can then take our course ID, tie it back here, and find out that Alex is taking a math course in the fall of 2018. Of course, we can do this with any number of students and courses. We can see that Clint is taking a database course in fall of 2018 as well. And this is much better than the alternative. If we were to combine all of these tables into one big table, we would have redundant data. And that's really bad. So we can see that in this table, you see Alex twice, you see his address twice. That means that anytime something changes, we have to go back and search through this entire database, this entire table, and make all of those updates. If, on the other hand, we stick with our separate table structure, all we need to do is update the address once. And then when we join these together, all the changes get pushed through. This is the heart of the relational database. This is how all data is going to be structured. All of the data you're working with for analytics is going to be set up this way. Now, the way we interact with data structured this way is through what's called a DBMS, a database management system. There are many different options: MySQL, IBM's DB2, Oracle. Each organization is going to choose a different version of this. They all work basically the exact same way. They're just slightly different software solutions. Some organizations like IBM will sell you a package deal that includes storage in a database structure and DB2 or something like that. So the summary of this is you're going to see different database management systems. The way you interact with the data is going to be the same across all of them, other than some small syntax changes. For our practice today, we're not going to install a new DBMS. Some of these are enterprise grade tools and are quite expensive. We're instead going to practice in Python, which has a SQL library that lets us code in SQL very easily. And that leads us to SQL itself. What is SQL? Well, it stands for Structured Query Language, and it is exactly that. It's a very highly structured programming language that's designed to acquire data. It's designed to pull data out of relational databases. It's been around for a long time, since the 80s. It provides lots of flexibility for pulling data, for analyzing data, for joining data. And it's got a very simple form. This is a full SQL query. This will do aggregate functions like averages and sums. It will take counts. It will let you reference multiple tables. And I'll walk you through some SQL queries from the very, very simplest all the way through to making something like this. Now, some of you may have heard of NoSQL or other big data platforms like Hadoop or data streaming capabilities like Snowflake or Kafka, and say, why are we still using SQL? There's more exciting technology out there. We should be doing that. And the answer is that actually SQL is still the most common. It's the most useful. It's fast enough. We know it works. It's been in market for over 40 years. Much easier to learn. And it turns out that if you're going to be using big data tools anyway, Spark, Hive, Impala, Hadoop, they're all based on SQL. So no matter how you're getting at your data, you need to know a little bit of this programming language. This is going to be how you become that citizen data scientist and be able to actually get data out of your organization. So when in doubt, always lean on the relational model and SQL. It is much, much simpler to set up than some of these more complicated platforms. At my past job at one of Canada's other banks, we spent over $150 million trying to bring in a big data platform for the organization. And no one wanted to use it. It's too complicated. Everyone went right back to using their old SQL relational databases. Eventually, the way we got people to use it was by duplicating our relational database structure in Hadoop. And yes, this company stayed alive. In Canada, it turns out that you can basically fail completely as a bank, and because no one else has any choices, you just keep going. 150 million is small for a tech project. RBC, where I work, we spend $4 billion a year on technology innovation. So yeah, it is very good to be a banker in Canada, yes. And we're very fortunate that we're spending so much money to try and make this better. The moral of the story here is jumping on the sexiest new technology, not always going to serve you well, right? There are battle-tested, very effective starting points for this that can still earn you millions and millions of dollars in value without having to, jump off the deep end and make huge investments if you don't know how they're going to turn out. Even at RBC and Borealis, where I work, most of the work we do comes from traditional databases, traditional data warehouses. Yes, we do advanced machine learning. Some of that is with unstructured data, but the vast majority of what we use comes from models like this. And even our PhD machine learning researchers use SQL every day. So let's write some SQL. Let's learn a little bit about this. Lots you can do with SQL. The heart of it is, this is going to be how you get your data out of a database. There's going to be a database with many tables hidden in the background. You're going to be able to go in and select exactly what you want. You're going to be able to do some analysis. And what I want you to think about is, if you could give everyone at your organization the power to run their own analysis, to be data-driven, how much better would that be than flying blind, than not making data-driven decisions, or than relying on a different team entirely to pull information for you, to give you simple answers, like how many customers bought a product yesterday? How many customers left our organization this month? Very useful questions. At the bank, where we have many customers, many products, many different departments, RBC has 85,000 employees. It's a very big organization. Many people at the bank rely on Teams. So we have to send an email off to someone and ask questions like that. Even simple questions like, how many bank branches do we have? You need to email someone needs to write this query, and then you get an answer back in a week. This is the wrong way to run a business. You want to wait weeks for all of your useful information. What we're trying to do now is give everyone the ability to write some SQL, give everyone access to this data, let them become those citizen data scientists, run the analysis themselves, empower them to get the information they need right away instead of ending up in a queue somewhere else. So this is huge for us. We run very similar training with everyone at our organizations. And it all starts with a database itself. So these two very small tables are available on Canvas. They are the examples we are going to use throughout this PowerPoint. They're very simple. We have a customer table that has a little bit of information around who you are, where you live, what date you joined the organization, and a status, a gold, silver, bronze. And then a transaction table. The transaction table has your customer ID, the date you made a purchase, and the value of that purchase. So very simplified database structure, but still normalized so that there's no duplicates across those tables. Right? This will be our rolling example. The data is available. I've already got it imported into a Jupyter notebook, so I can show you a little bit about what this looks like. And then the first thing we do in SQL is select data, the simplest query. The syntax, the simplest way to get data out of a table, the syntax looks like select the name of columns from the table that information is in. If we think about our first example there was a customer table. Perhaps we want to select the name of all of our customers from the customer table. Right after select, we include our column names. Right at the end, we include our table name. You can do very simple ones like this. You can include as many columns as you'd like, whether it's 1 or 5 or 10. And of course, you can reference any table you want. A few shortcuts in SQL. The asterisk or the star is short for every column. If you select star, you'll get every column in a table. SQL, generally speaking, is case insensitive. So you can put capitals or lowercase letters wherever you want. And you can do a whole bunch of extra aggregations, include extra columns in that select statement. It's very, very flexible. You could pull the same column twice if you wanted to. You can even do math in a select statement. You could say, give me the transaction date plus the amount that they spent. You could add those things together. Or you could take an average of all of the purchase prices of a product. I'll show you what those aggregations look like a little bit later. The point is very, very flexible, very simple structure here. I'm going to flip over to the Jupyter Notebook quickly and just show you a couple sample select queries here. So in this Jupyter Notebook, all I've done here is the same data import we've always done. I've imported the customer file and the transaction file. And here's what they look like. This is exactly what it looks like in that PowerPoint. We've got our customer table down here and our transaction table up here. Now, to write SQL in Python, we need a new package. It's called Panda SQL, and it's made by the same people as Pandas. You will have to install this. It is a non-standard package, so you will have to install it before you can use it. You can install it using the instructions I gave you last week. When we break out into teams, if you're struggling to install this, either myself or one of the moderators will help you get this started. Once you've imported Panda SQL, all we need to do is write a query and print it. This is the syntax. This is just an object I've called query1. We reference Panda SQL, period, SQL df, and for SQL, short for SQL data frame. And then in quotes, we put our standard SQL query with a semicolon at the end. In this case, I've asked to see the date column from the transaction table. And if I run this, I get my date column from the transaction table. I can change this to anything I'd like. So in the transaction table, we have a column called total. We can ask for both. I can ask for total twice if I want, and it will reproduce the exact same column. As I said, you can do basic math in SQL. So what if I asked for total plus total? Well, it's just going to add up the total column twice. If I change this to customer, let's say, and try and run it, it's going to give me an error because my columns don't match. No such column date. That's the error it's trying to give me. So we always need to make sure that we're matching up our columns with our tables. From our customer table, I might want to see information like name, city, and province. And now I can see this subset of my customer table. So that is the simplest SQL query. This is the easiest way to get data out of a database. If you just need everything available to you, just select star, it will print out the whole database. But I do have to warn you, tables get very, very big, and Python and SQL are dumb. They will do anything you ask them to. That means if you select star from a massive database, it will try and print the whole thing. And it may take hours or days to complete. When I first started my career as a data scientist, we would all write our SQL queries during the day. We would run them before we went home for dinner, and we would hope that they finished by the next morning when we got in. That's how long these used to take to run. Now things are much faster, more efficient. But when I grew up, that's what we did. All of our queries ran overnight, and you'd better hope that you got the query right, because if it errored out at midnight, you lost an entire day of work on that data set. Things are better now. My warning to you is be very careful about select star, because SQL and Python will do exactly what you tell it to, even if what you tell it to do isn't that good an idea. Okay, from selecting data, we might want to consider a few other things. One is removing duplicates. Databases have a tendency to build up duplicate values. And this is partially because of how we store data. For example, when we add new customer information, so when I go in and I change my address at the bank, instead of overwriting the old record, sometimes we'll add a new one. And that way we have this history of every place I've ever lived. So now we have multiple records with my name and my customer ID. Of course, if you wanted to do some very simple analysis, like find out how many customers you have, well, you're going to have duplicates in here. And we don't really want that, right? We don't want duplicate values. Fortunately, there's a very easy way to remove duplicates, and that's with the distinct clause. So if you put select distinct before the columns you want to select, it will only pull records that are unique. Any duplicate records, it will drop. So a little bit of handy syntax here for you in case you have duplicate values. I'll show you what this looks like in a little bit. You can include it for any column you'd like here. The next one I want to show you is sorting. When you query a database, the data is going to come back in an arbitrary order. Sometimes you're going to want to see your results sorted in a specific way. So you can tell your DBMS or Python how you want your data sorted. To do that, we write our standard select statement, select the columns we want from the table, and then we say order by. We give order by a column we'd like to sort by, and that lets us sort our transactions. There's two different directions you can sort, ascending and descending. Ascending counts up and descending counts down. So this bottom query here would select all of the columns from the transaction table, and it would order them by the total value descending. Sometimes you're going to want to break ties. If there are total values that are the same, you can add another column to sort by. In this case, we're saying select all the columns from the transaction table, order by the total value, and then order by date, both descending order. Let me show you a couple examples of this. So we'll add a new cell here. We'll call this query 2. Let's select distinct first, and we'll say, let's select the distinct status from the customer table. And we can see that what it's done is just returned gold, silver, and bronze once, despite there being multiple records of both gold and silver here. So that's only going to return unique values. That's what select distinct does. It will work on anything else. We could do select distinct province and see that there's only 2 provinces here where people live, 3 provinces, sorry, where people live. If we wanted to do a little bit of sorting, we could say, show me all of the columns from the transaction table and order by the total value. And now we're going to see that we can sort everything by the lowest value first, all the way to the highest. All we need to do if we want to flip that is add this DESC, short for descending, and we'll flip the order there. As I said, there are sometimes duplicate values, and you may want to break that tie. So you can go in here and say order by total, and then order by date descending as well. And that will flip the order around here. There's a question in the chat here. Is it possible to interrupt a long SQL query? And the answer is yes, you can interrupt any Python query that's not working properly. This stop button here will interrupt anything that's currently happening. So you see sometimes when I run this, it happens very, very quickly, but this turns into an asterisk. If that's an asterisk and nothing's happening for quite a long time, you may just want to stop everything, look at your query, fix it, and go from there. You can also click on this kernel option up here and say restart and clear output. This will reset your entire Jupyter notebook. It will clear all of the output you put together, and it will stop anything running in the background. Hopefully you don't need to know that, don't need to use it, but it's good to have just in case. Okay, we have been going for an hour straight. So there's one other question in the chat. Yes, absolutely. You can use several databases, several tables, all at the same time. We're going to start simple with these SQL queries, and we're going to move up to more complicated ones where we're joining tables together in the end, pulling data from across different tables and databases. The syntax, fortunately, is quite easy to expand from database to table to column. And you'll find it's very, very easy to pull data from different sources all into one data set that's ready for analysis, whatever you need to work on. Okay, we have been going for an hour straight, so I'm going to propose we take a 10-minute break. I will see you back here at 7:10 or so, and then we'll jump back into doing some SQL.
Ребят, всем
Всех
привет.
подключили, привет. Или все сами ушли?
Да нет, кто-то подключался.
Привет, привет.
Всем привет. Вот
Привет, привет.
люди.
Я воскресли сразу, да?
Андрей там в галстуке. Вот. Денис там нарядный. Денис, ты все с отдыха вернулся?
Все, кончилась жара,
Мы
началась.
видим тебя загоревший, отдохнувший.
Не знаю, насколько Zoom.
Working through those cheat sheets, the data exploration cheat sheet, and then the smoking exercise. That exercise, I just showed you the solution to earlier today, and it's posted on the portal. That was all you had to work through. In terms of assignments for grades in the course, there will just be one team assignment that you'll work on that we'll post soon and will be due towards the end of class. What we do in class is just for you to learn. You don't have to submit it. You don't have to send it to me. You can if you'd like. I'll put out a couple exercises each week. They're for you to get practice.
Okay. Thanks.
No problem. Okay, let's jump back into our PowerPoint. One of the really powerful features of SQL is filtering. Filtering allows you to select rows that match some sort of criteria. For example, if you wanted to see all of the customers from a certain city or province, if you wanted to see all of the customers that were not in a certain area, or where a certain group of customers that spent over a certain amount of money or under a certain amount of money with your company. For that, we use the where clause. Our regular SQL statement doesn't change. Select the columns we want from the table we want them from. Then we add where. When we add where, we just put in some statement that we want to be true. This first one, we say where province is equal to Ontario. That'll return all the customers from Ontario. In this last one, we say where the total they spent is greater than $100. It's going to give us all the customers who spent that. This is where we can really start to take very, very big databases, very, very big tables, and get them down to just the subset we really care about. There are a number of different operators we can use as part of a where clause. You can use the equal sign, equal to a value. You can say not equal to, so everything but a certain group, greater than, less than, and then a few extra ones like between, like, and in. And I'll talk about each of these. These let us basically combine other types of operators together to make things a little bit easier. I will show you a few of these examples. Let me do them in a group. So I'll walk you through like and between, and then we'll do a couple together. The like operator lets you add what we call wildcard characters. So sometimes you don't need to match an entire group, but you want to match part of it. We can use the percentage character to mean any number of characters of any type. And we can use the underscore character to say any single character. I'll show you what this looks like. If we wanted to see all of the customers whose first name was Alex, we could say, select star, show me all of the columns from the customer table, where name is like Alex percentage. And this percentage sign means any number of any type of character. So this would work for my name as well as any other Alex in the class. You could also say, we want to find all of the Susan Anthonys with any middle initial. Susan A. Anthony, Susan B. Anthony, Susan C. Anthony. So the underscore represents just a single character, and it can be any character in that space. This query here, select star from customer where name like percentage B percentage. This is going to show every row where someone has a B in their name, because it will allow any number of characters before B and any number of characters after B. Anyone with a B in their name is going to show up for this one. The like operator is very, very flexible because it allows you to select for any set of characters. Allows you to find patterns as part of your where clause. Some examples here. If we wrote a query like, select star from this table where city is like percentage sign ON percentage sign, well, we would look through this city column and see that Kingston has an ON in it, so that's going to work. Toronto has an ON in it, so that's going to work. Edmonton as well, the ON right here. But Vancouver, that won't work. There's no ON in Vancouver. So this will return everything except that row for Vancouver. This pattern is a little bit different. This is only going to return rows for cities that end in ON. In this case, that's just Edmonton and Kingston. Toronto has ON in it, but not at the end. We did not allow for that percentage sign at the end of the word. And the last one, ID like 1 underscore underscore 1. So this will let us take any set of customers that start and end with a 1 in ID. That'll work for this ID right here for Alex, and this ID right here for Donald, but that's it. Will only work if there's a 1 at the start and a 1 at the end. Anything you want in the middle. These are the wildcard characters. This last one, anything that starts with a 1-1 and ends in any number of characters after, that will only be Donald here. It's the only one that starts with a 1-1. If we were going to do this, write a query to select customers who come from a province with the letter B in it. Well, we would want to create a query that had that percentage sign on either side of a B. Right? That way it would capture both AB and BC. The between operator. So like allows you to build patterns in, use wildcard characters. Between can make sure that a value is between two other values. So it's sort of like combining a less than and a greater than sign. It works for numbers. So show me all of the transactions where the total was between 0 and 100. The syntax is very easy. We use our where clause again. We reference a column. We say between a number and another number. Not only does it work for numbers, but it works for dates, which is very handy. So we could say, show me all the transactions that happened between February and March, for example. And all we need to do is match this date format. So between, very powerful, very, very flexible. One thing I will say is that dates are a very tricky data format to work with. Every tool has its own date format. That means that sometimes when you're taking data from Python and moving it to SQL or vice versa, the dates won't work out as you expect. This is not such a big issue at large organizations because generally the dates are fairly well structured. But if you're getting data off the internet, for example, different countries have different date formats. It can be a little bit tricky to line them up sometimes. So don't worry if your dates don't work out. There are some tips and tricks to make those work a little bit better in that data exploration cheat sheet. Okay, once again, which rows match these criteria? So customer, you can interrupt me anytime when there's sometimes you just miss it. Yes, yes. Yes, absolutely. So the question was, can we return the customer who has purchased the most number of times? The answer is absolutely yes. You will need one extra technique that I'll show you in just a little bit here. You need to use a technique called a subquery to do that. But you can write a SQL query to return basically any subset of this data you want. It's a very, very flexible language. So yes, absolutely, you can do that. Another question in the chat, what's more efficient, Python or SQL? Hard to say whether one is more efficient than the other. There are 4 different things. So SQL, generally speaking, is for working with very large databases. And it's probably better than Python at that. So if you're looking at very large databases, massive relational databases, you're going to want to use SQL over Python. If you're working with big data and you want to use something like Spark, you're going to be much better than SQL in that case. And then for data that you can reasonably work with on your computer, Python is going to be, we'll call it more efficient because you can keep everything contained in Python, but they've really got different use cases. What I will say is that because you can write SQL queries in Python, most people stay in Python all the time. So you load Python up once on your computer, you connect directly to a database, you write your SQL queries in Python, pull your data in and work from there. It used to be the case that you'd actually go into a DBMS like MS SQL or MySQL and you do analysis in there. I don't see that so often anymore. Most people just stay in Anaconda and Python. I think there's one other question in the chat. To write SQL in Python, you will need to download a package called Panda SQL. If you're on a Mac, you can open up Terminal and type conda install Panda SQL. And if you're on a Windows machine, you're going to need to open that conda command prompt through Anaconda. The instructions for that are in the first cheat sheet from last week. If you don't know what I'm talking about, that's fine. When we break out into teams, ask for help right away, and we'll help you get that installed. All of this code will be posted after as well, so you can run through it. I'll try and post it while we're in our breakout rooms, so you can work on it right away. If you want to use a proper database management tool, then yes, it needs to be installed. You would need to install MySQL or whatever tool you want to use. Okay, a few between queries here quickly. This one is asking us to find all of the IDs between 1002 and 1006. And remember that these are numbers. So it's not that we're going to get all of the records from this value to this value, but instead we're only going to get Peyton, Bobby, and Johnny, because Donald Trump is larger than 1006. So it's not in row order, it's in numeric order. These just happen to be unsorted. Dates between 2014 and 2016, we can figure that one out. That's going to be Peyton and Donald. Between clauses are what we call inclusive. So they include the values you write here. That means that January 23rd, 2016 will be included in this query, always inclusive. The last one I want to show you is the in operator. The in operator is a way to test for multiple conditions. So we said something like where customer ID is equal to 1001. Well, what if you wanted to find all of the customers with 500 different customer IDs? Well, you could include them in an in statement. In this case, what we do is our same select statement as always, select star from transaction, where ID is in the set of 1001, 1006, and 1106. All we need to do here is say in, open brackets, and then any of the values we want to see. This allows you to stay out of the sorted order. So you don't need to use a greater than or a less than, but can instead reference any values you want. Here's another example from two different dates, only February 1st or June 23rd, nothing in between, just those 2 days. In this example, we've added a not in front of in, which is just the opposite. It just reverses that. So if we said province not in ON or AB, well, that's only going to leave BC for us. In gold and silver, well, it's going to return everything except Donald. Let me, one last thing before I do a few lines in Python is you can specify multiple where criteria. You can use ands and ors to combine these. So we could say, show me all of the transactions where the total is either greater than 100 or less than 200. That's the same thing as saying between 100 and 200. You could also ask for all of the customers who are silver or bronze in Ontario. So you can see how by doing this, we can get more and more specific about our queries to start really running some analysis on this, starting to really understand our customer base. Let me show you a few of these in SQL. All right. Let's write a couple where statements here. So let's see all of the rows from the customer table where status is equal to gold. Let's try something else. Where customer ID is equal to 1001. Well, it really doesn't like that. There we go. One customer with the ID 1001. So we can use this where clause to identify single records as well as many records. If we wanted to see all of the customers from the province Ontario, we would just change this to province and Ontario, and we'd see all of those customers. We can, of course, combine this where province equals Ontario and status equals gold, for example, and get all of the intersections there. We don't need to use just equal signs here. We can use any sort of operator. So we could say where ID is greater than 1002. And that's going to return all of the records that are greater than 1002. And all of these clauses can be combined together. Right? So we can say where ID is greater than 1002 and order by status. And it's going to reorder a status in alphabetical order. All of these things can be combined together into one big query. Between works just the same way. We can say between 1001 and 1002. Sorry, I forgot the where. There we go. We always need to include that where when we're going to use a between or a like or something like that. And this is going to give us our inclusive set between 1001 and 1002. So where is the clause we're going to use to filter by rows, and select is what we're going to use to filter columns. That's going to give us the ability to basically select any full set of rows or columns from any big table. Now that we have that background, we can move on to some of the more fun stuff. Okay, aggregating and grouping. This is where we get to start doing some real analysis in SQL. And SQL actually has built-in aggregate functions like sum, average. This means that we can go in and we can start doing analysis on our customer base and on our data instead of just pulling records. That's what we were doing before. Yep. Yes, between is inclusive by default. These, it looks like there's a follow-up question. You cannot change it. Instead of changing it, what you do is you just move the value up or down appropriately so that it's sort of like the difference between less than and less than or equal to. Okay, no problem. So these aggregate functions are really, really powerful tools. The most common ones I see are sum, average, min, and max. Really, really handy here where we can go in and, to one of the earlier questions, start finding out who's purchased the most, for example, the max number of purchases, or what's the average purchase amount for a group of customers or a single customer. The last one, the last aggregate function is a little bit different. It's the count function. And the count function lets you count how many rows exist in a certain query. So that might be useful if you wanted to know how many customers or how many total purchases you had. The way we use these aggregate functions are just by embedding them right in the select statement. Instead of asking for select total from trans, which is going to show us all of the total values, we just say select sum of total, and it's going to add them all up for us. These are all the aggregate functions that are readily available. Some database tools have extra aggregate functions, like median, for example, but not everyone has that. The extra ones that I've sometimes seen are median and quartiles, which let you do the values at 25, 50, and 75% if you order them from low to high. I'll show you some of these when we get back. I'll do them in batch. The count function does exactly what it sounds like. if we went in and ran a query like select count star from trans, it will show you the total number of rows in the transaction table. Where this gets really handy is in including where clauses in there. Now we can start figuring out how many of our transactions were greater than $60, or how many really low value transactions do we have? You know, transactions less than $20, for example. When using aggregate functions, you have to be careful. This is because when you're aggregating, SQL is only going to return one row. It makes sense, right? If we're asking for the sum of a column, there's only one value. So what happens when you write a query like this? You say select customer ID and the sum of the total column from the transaction table. Well, there are many customer IDs, but only one total, one sum of total. So you're only going to get one row. And the problem is it's going to give you a random customer ID. It's not going to have anything to do with that sum you asked for. So the rule is, if you're going to aggregate any column in your SQL query, you need to aggregate all of them together, unless you use a function called a group by. So either you need to make sure you're using an aggregate function like sum, average, count on everything, or you can use a group by. And a group by is one of the most powerful tools in a relational database. Here's how it works. Let's say we wanted to know the total sum of sales for every customer. You might think, okay, well, let's select the customer IDs, the sum of the total from the transaction table. And because we know we have to either have only a single record or aggregate everything, we could include a where clause and say, show me this for customer 1001. But then you'd have to write this query for every single customer at your business. And that wouldn't really make any sense. You wouldn't do that. Instead of that, we can change that where clause and say group by. And we can include any column we'd like to group by. In this case, we're going to use customer ID again. And what this is going to do is tell SQL what we actually want to see is the total, the sum of total for every customer ID, not just one, but everyone. So let me show you how this would work from a table perspective. Here we have our customer table, and we're going to run this query here. Customer ID, the sum of total, grouped by customer ID. The first thing that happens is SQL goes out and it finds all of the unique customer IDs. In this case, 1001, 1002, 1004. That's them there. And then it records those in a new table. The next thing it does is it looks for every unique customer ID and sums up the total columns. So now it's moving over to the right-hand side, summing up all the values in total, and then writing those back to a table. So the group by lets us do analysis on an entire column with an aggregate function. Very, very handy. Great way to do some broader analysis here and not have to type a where clause out every single time. So the rule is here, anytime you're going to use aggregate functions, make sure you're aggregating everything together or using a group by statement. I'm going to show you one more thing before we do some practice in Python, and these are subqueries. One of your earlier questions was, could we find the customer who purchased the most frequently? You need a subquery for this, and I'll show you why. If we wanted to find the customer who joined our company the earliest, the first purchaser of a product, we might try a query like this. The problem with that is it doesn't work. There's a few issues. Min, being an aggregate function, is only going to return one row. So what happened if more than one customer joined on that first day? we're not going to see both. Because there's an aggregate function, we need to aggregate everything somehow. And in this case, ID and name are not aggregated at all. The solution in this case is to use a subquery. A subquery is exactly what it sounds like. It's a query nested in a query. Here's what it looks like. In this case, we're going to write a query that says, show me the ID, the name, and the joined date from the customer table, where the joined date is equal to another query itself. The way I always think about these is queries run from the outside in. So your subquery is always going to run first, and then your big query is going to run second. What's happening here is we're running a simple query to get us the earliest joined date, and we're plugging that in as part of a where clause in a bigger query. The way this would work out, let's say the earliest date was January 1st. This would change into January 1st, and then just represent another where clause that lets us select rows. Subqueries should always return just a single column. If you're returning subqueries with multiple columns, things are likely to break. So subqueries and group bys are ways of getting around this aggregation restriction, where either everything has to be aggregated or you need to come up with a more clever solution for getting at your data. I think there's another question in the chat here. Yes, so to join tables, you do need some additional code. I'm just going to show you a subquery here quickly, and then I will show you how to join tables. So say we wanted to find all of the purchases that were above average. Let's show me all the customers and their transactions that were above the average transaction amount. Well, the first thing I need to find, the thing that's going to go in my subquery, is going to be that average purchase amount. So I'm just going to write that one out for us. Select average total from the trans table. And I know that's going to be part of my subquery. So I'm going to go back to the start and write a new query now. For this one, I'm going to say, show me everything from the transaction table where the total value is greater than what this subquery returns. The way I read this is this query will run first. Our subqueries always run first. This is going to return the average value from the total column. And then this is going to return all of the columns from the transaction table whenever total is greater than the average. And what we're going to see here is just a subset of those tables, a subset of those rows, only 4 rows from the total here, because only 4 are above average. You can use these subqueries to do all sorts of clever things. This is just a very simple example. Okay, now the heart of the relational database is really the ability to join tables together. I wanted to get through all of these other things because this is the most complicated syntax for SQL that we're going to talk about today. Obviously, what we want to do is be able to take all of the different tables in a database, perhaps tables from multiple databases, put them all together and pull all that information out. And we know we need to do this because we normalize our databases so there's no overlap between tables. The motivation here is, in our simple example, what if we wanted the names of these customers or where they lived? You would obviously need that to send out the order, for example. We need both tables, so we need a join. Here's how a join works. If we think about our transaction table on the left, when we run a join, we append, in this case, the customer table to the right-hand side. And in effect, we duplicate a fair bit of data. Our customer table is actually much smaller than this, but we can see that customer ID 1001 is ordered 4 times. So all of this data gets duplicated 4 times to line up with these transactions. This new join table is the result of matching everything up. There's different kinds of joins. I'll talk through that, but the first thing I want to show you is the syntax for this. So a few extra pieces here. Our select statement stays the same. Select the columns you want from the table you want it from. We then add this join operator. We say join and give another table name. What we're saying here is show me all of the columns from the transaction table joined on the customer table. And then we need to tell SQL how to join the tables together. There has to be a way to match up a column from each table so SQL knows how they fit. In this case, what we're saying is look at the transaction table and find the customer ID column. And anytime that's equal to the customer table's ID column, match them up. You'll notice that there's a bit of extra syntax here where now we have this table.column name set up. That's because you can have multiple tables with the same column name. So now we need to tell SQL which table and which column we want. I think there's a couple things in the chat for me. Okay. Okay. So our new syntax is select whatever we need from a table we want, join another table to that, use this on command, and then tell SQL which columns match together. This one's fairly straightforward. Both of our tables have an ID column that references a customer. That's where we're going to want to match them up. Now, there are a few things that could go wrong here, right? We could have examples where the IDs don't match up. So we'll have to talk about what happens when they don't fit perfectly together. Earlier, someone asked about using multiple databases. This is where you can very easily use multiple databases. The syntax is database, period, table, period, column. So you can add multiple databases to this join as well. You can also join multiple tables together. Just keep using more joins and keep telling SQL how to match all of the tables together. So you can do this for every table in your database if you want. In this case, we can imagine there's an extra products table. And all you're doing is you're lining up those matching keys across all of the tables together. And that's going to return all of the information for you. Now, there are actually different kinds of joins. There's 4 different kinds: inner, outers, lefts, and rights. The inner join is what happens by default. It's by far the most common. It's the most efficient to run. The inner join only returns records where the IDs match on both tables. So anytime, say there's a customer without an order or an order that doesn't belong to a customer, it just will not show up as part of this query. An outer join is the exact opposite. It's going to show every record from both tables, even where they don't line up, and it's going to fill in any missing data with null values. Left and right joins speak to which table is going to be the master table. In a left join, the left table is the master table, and it's going to show you all of the records from the right table that match. If there are extra IDs in the left table, it will fill in the difference with nulls. I'll show you what each of these look like. What you should know is that inner joins, most efficient, most commonly used. Full joins or full outer joins are the least efficient queries. They're very expensive to run. These are the ones that take overnight to run if you've got very, very large tables. Here's what they look like. I'll show you an example, a rolling example for us. So let's look at these two subsets of the transaction and the customer table. We're doing an inner join here. And if we look at our customer IDs, we can see that 1001 exists in both, 1002 exists in both, but 3 and 4 don't exist in both. They only exist in one table. If we ran our join query, select star from the transaction table, inner join on customer, and match up these two customer IDs, this is what we would return. Only IDs 1001 and 1002. 3 and 4 get excluded because they don't match perfectly. If we did a left join, and when I say left and right, I actually mean the table that you reference on the left-hand side of the join and the right-hand side of the join. That's the only difference. They're actually the exact same. You can just flip the tables around and get the same result. The left outer join keeps all of the observations in the left table and lines them up with the right table. In this case, we have 1001, 2, and 3. So we're going to see all of these customer IDs in the resulting table. You'll notice that 1004 doesn't show up here, so we won't see that. And that there's no matching record for 1003. When we run our query here, we're going to find that it just fills in null values for 1003 because it can't match it to anything. We've told SQL we must join from the left-hand table. It did the best it could. There was nothing matching, so you get null values. Alternatively, if we did a right join, which is now using this customer table as the primary table, we're going to get 1004 show up on the right-hand side and nulls over on the left because there's nothing to match it to. Left and right just refer to whichever is the primary table. And the last example here, the full outer join. This keeps all of the observations in both tables. So we're going to have nulls on both sides. We're going to get nulls over here where 1003 doesn't match on the right, and nulls over here where 1004 doesn't match on the left. That's why this is the most expensive. It's because it returns every single row from both tables and has to check for matches for every row and fill them in where they don't exist. I think there's a question in the chat for me. I think I understand where this is going. So the process, the way this fits into the bigger data science picture is you want to do some analysis on your customers and their purchases, for example. And all that data is stored in a database across multiple tables. Hopefully not 100 tables, but maybe 5 or 6. In a simple case, what you might want to do is pull that data together and produce some visualizations. We'll talk about that next week. Put some charts together, talk about how different customers behave differently with your organization. In a more advanced case, you might want to build a model that predicts how much Alex is going to spend at your organization. In either of those cases, what you're going to need to do is write some SQL, get the table of data that you need with some joins, some where clauses, etc., and pull that into Python. From there, you'll very easily be able to create visualizations, build predictive models, run analysis very, very easily. So this is sort of the first step in the data science process, actually pulling your data into an analysis tool. Okay, so there's a little bit of extra material in this PowerPoint. If you're interested in learning more, I've got some queries in here on how to create tables, modify them, delete data, things like this. I find that they're not that useful from a data science perspective, but I wanted them in there for completeness. Now, there's one last thing I want to talk about, which is query performance and efficiency. And then after that, we'll break into our groups and do some exercises. Query performance is a pretty big deal. Like I said, there was a time where we actually let these run for 12 hours overnight to finally get our results. Things are a little bit better now, but not always. So it's important to think about how efficient your query is before you run it. And if you do find that your queries are taking a very, very long time to run, there's a few things you can consider. For truly huge data, you may want to move off onto different technology. When you're at that scale, start thinking about Hive and Spark or NoSQL solutions. That's totally fine. For a regular database, you might ask your database administrator to denormalize some data or to create indexes. These are sort of last resorts, but let me tell you a little bit about them. An index sort of creates an address book for tables. So imagine an important column in your table being the customer ID, and they're randomly sorted throughout your entire table. Well, an index would give you an address book of these things and make it much faster to find those individual customer IDs. So it would tell you that customer ID 5001 is actually in row 100. Very fast to identify these things. And denormalization is when you start duplicating data across tables. It's risky because it creates data integrity problems, but it makes your queries run much, much faster. The things that really slow down your queries are lots of joins and big tables. If you're doing lots of outer joins, if you're working on really big tables, that's what's going to slow you down. Other than that, you'll generally find SQL is pretty fast. It's a pretty efficient tool. Okay, that is all I want to share with you about SQL. There is extra material in the PowerPoint if you're interested in that. I will very shortly post the solutions to all of the exercises I showed you in that SQL PowerPoint. For the rest of class, I wanted to leave lots of time for practice because I know some people had technical problems last week and did not get through all the material. So for the next 2 hours, we're going to break into our teams. Anything that you weren't able to get to last week, let's spend some time on that. We have our moderators here as well as me to help you work through that, help make sure Jupyter Notebooks are working okay, help you get through some of that code. And then on Canvas, under Module 2, there are 2 SQL practice problems for you to work on. One is called one is at the very last slide of the PowerPoint. It's called practice question, and it uses a data set stored under Module 2 on Canvas. And the last one is called SQL challenge, and it has 4 data sets embedded there and something to work through. So you're gonna have to do joins in multiple places and pull things together. None of this has to be submitted to me. It's just for practice in your team rooms. continue to get comfortable writing code, writing some SQL. We will break you out shortly. If you have any technical problems, if you need help installing Panda SQL, there'll be a button that says ask for help at the bottom of Zoom. Just push that right away and one of us will come and get you sorted out. Now, before we go into breakout rooms, any questions from anyone on today's material, last week's material, anything else? All right, well, if there are questions, please let me know, ask for help, and I will come visit right away. And Margarita, I think we can break into our teams. I recommend everyone takes a 10-minute break just to recover and then get started.